All right. So, well, maybe I should discuss a little bit about what. Let's see. Let me just go ahead and take a picture of this. Erase. Just troubleshooting with a client.
Okay.
Retrace the steps. Okay. So, first thing we should think about is what is it that our equipment does, okay? So you might heard some of the buzzwords, ERT, electrical imaging, resistivity imaging, things like that, right? So what does that mean? Well, if we had the ground here, and
Yeah, we'll grab this one.
sure.
It'll be easy to remember. A lot of information and get it back in.
So it's kind of what we were talking about on the phone.
Okay.
So, first thing is, all right, we create electric fields, okay? That's what our equipment does, and it happens to be that there's a, when we do inject a current into the ground, there's an electric field that's static. We hold it kind of at a steady state. We inject a constant current in there. Now the current you have to think of as, you know, electrons flowing through, right? And there's such a thing called current density. That basically means that the current wants to go through preferential pathways. It will go through all of the material, but it will have a distribution to have more electrons going through conductive pathways versus areas where it's more resistive and it wants to avoid that, right? So if we can do a very simple case, and that is, let's say, just have a homogeneous earth, okay? That means that it's just one type of material, okay? It could be like just a constant resistivity, like sand, a very well-sorted sand. So if that's the case, then we have a very symmetric electric field. So if we call these the transmitter, we call those electrodes A and B. So these just represents a stake that actually goes in, penetrates into the ground a little bit like this.
Mm-hmm.
Okay. For all intents and purposes, we can assume that this is a point source and not a rod. Okay, because the distance between these are sufficiently large enough that this appears to be a point source. Okay, so we inject current. It doesn't matter the polarity, but let's say we inject current. So you get this kind of like onion shell looking thing like this. And of course this electric field exists everywhere in the earth. Just to note, I put this vector field like that, electric field. So this describes the amount of current, the density, right? So are you familiar with contour lines? Kind of like on a map or?
Okay.
Okay, so like on a map, the contour interval, if it's really close to each other, that means it's like there's like some thing that's either going up very steeply or, you know, going down. It's like the rate of change in the slope, right?
Okay.
Okay, but an electric field, so basically what this means is that the lines up here become like denser, right? Because this is like the path of perhaps the least length, right? So let's just say this is symmetric, meaning that this is uniform, right? Well, so what happens then is that to take measurements of this, we don't know where this we don't know what it looks like. We don't know where the electricity is going. We just know it goes from this point and comes back at this point, right?
So essentially, it's infused or injected at point A and then received at point B.
So what we're interested in is the amount of current. Okay, it's just, this is Ohm's law here. That just means voltage equals the current times the resistance, right? So this is like volt, this is current, and this is resistance. Okay. So basically we apply some voltage, and injecting current,
Okay.
okay? And this current is injected. We just know what that amount is, right? We don't know where anything is. So what we do is on the surface is that we set up a number of electrodes, stakes here. That's usually most often it's a uniform spacing, okay? The reason we do this is that we want to measure a field called the potential field. It's coupled to this. So the potential field is actually, the field lines are perpendicular to the electric field. So all these, even though my drawing is not very good, imagine that this describes, I'll explain this in a second here. Like this. This describes a potential field, whereas the way that you know it is voltages, right? You might have heard of a 12 volt car battery, right? So that has a 12 volts or 12 volts potential, right? So if we measure between these, these lines, now they don't exist in the ground, this is a graphical representation, right. But the fact is that they're equipotential. That means that if I were to measure on a line like this, I would get a 0 voltage, but if I measure across them, I will get whatever, let's say if we call this 1 volt, so that would be from here to here be 1 volt, then over here be 2 volts, right?
Okay.
Okay, and so forth, so forth all the way through here, like this. Well, so now remember this is like uniform field, so we might measure, we call this the receiver here. The voltage, and we can measure them at any number of these dipoles there. Different sizes. We'll call this the transmitter, and we'll call this the receiver. Okay, our instrument has 8 of these in there. Okay. So for every time you transmit, you can measure on 8 dipoles, which means you can measure like from A to B, one shot. You measure over here, another reading over here.
Only 8 at a time.
What's that?
8 at
a time.
Okay.
It's 8 channels.
Okay.
Okay. But what's important, I guess, is that in our system we have 8 dedicated receivers. There's ways to cheapen the product by taking an A to D, which is what converts the voltage to digital numbers that we can actually manipulate and number crunch, where you can multiplex it out over many different channels, but you sacrifice resolution and accuracy, that kind of thing.
Okay.
But so what happens here is that these equipotential lines are kind of evenly spaced, even though I didn't draw them very well, and they describe this potential field for this location. So one location is not going to give us enough information on the Earth, right? Mm-hmm. So we move, once we've defined the potential field as much as possible around A and B, the transmitter, we move it. We create a new electric field somewhere else. Okay? And each location is unique. Okay? What's not, what that may be changing, but what's not changing is what the ground is like in the property of resistivity. Well, you know what, I need to back up. Resistivity, we should define what that is. You've heard of resistance before, resistors, things like that. Resistivity is a bulk electric property of all material. That means all material exhibit this property. And what it defines or describes is the ability of some type of a material to inhibit the flow of electrical current.
Okay.
So if it has a high resistivity, it means that it wants to really inhibit the flow of electricity through that material. Okay. If it's very conductive, that's on the other side of the scale, or you could say very low resistivity. That would be like things like copper, salt water, things that are very conductive that will readily lead electricity.
Okay.
Okay. In the ground, we don't know what the ground looks like, so we're going to try to figure out the resistivity distribution by making many of these measurements. Because each one of these measurements we can actually solve what's called a finite element mesh. We actually mathematically solve the physics of this problem. And it's a very huge computational problem, so it could take a very long time, like in orders of several weeks if we don't do it in a well thought out way.
Okay.
So what our system does, it automatically collects this data for you, so you don't have to do it by hand.
So essentially, when it comes to conductivity and resistivity, so if you have a piece of copper in the ground, and you know that copper's resistivity is X.
Yeah.
The system will say, okay, this is, or it'll show it in numbers, it'll say, this is copper, and then if it hits a piece of wood, you know that it's Y, and then it'll say
Yeah.
that's what it is.
So that's right. And what's so nice about the resistivity property, because all material exhibit this, is that you can define a range for each type of material.
Okay.
Okay, but on the phone we talked a little bit about what we're actually measuring. The resistivity is largely due, there's several factors that contribute to the resistivity response. You know, the type of material, but a lot of it is the porosity and the water content of that material.
Mhm.
For example, like a limestone will be different from a sandstone or sand or a gravel
Mhm.
or a granite, which is, you know, crystallized rock, or crystalline rock that is has very little pore space. So you may see in one area, may see a sand and gravel that is fully saturated with water. Well, then it's going to have a lot of water for electricity to flow through. In another case, it might be above the water table where it has no water and it's really dry, and then it will exhibit very high resistance properties. So some materials overlap a little bit here.
So then, if we're looking at an area that has very little water,
Yeah.
it'll be a different application than it is in, say, a sandy area or in a just like a turf land.
Well, what will happen most likely is that the resistivity values for each area will basically move along a scale, kind of like, because regardless if you're, if this geologic model that you have, for example, if it's above the water table, it's very dry, let's say sand here, and then you go to some other location, well, the material properties are different, so even if you apply water to all of it, or moisture, then they're still different from each other, so
Okay.
you still see that kind of thing.
Okay.
But the issue I think that you have to think about here is that in geophysics, very few things actually directly detect certain materials. There are some things that you can directly detect. We mentioned a little bit about ground penetrating radar. It's a very, very nice technique used in geophysics. But some of the limitations is that the electricity here, for example, in our example, is if I have a very strong conductor near surface, let's say, you know, clay or something. Well, for me, my electric field lines will start dipping in here, following this clay and coming back this way, right? So the electric field will look different. Let's draw that. Actually, let's make it an even easier situation here that's very intuitive. So first you have to understand that ground penetrating radar has a different phenomenon than what electrical imaging does.
So GPRs work basically like a what do you call them? An ultrasound type application, right?
Like a what?
Like an ultrasound. You know how they do like X-raying for kids.
It would be analogous but completely different.
Okay.
Okay, the analogy is really that in like a ultrasound, you're dealing with very high frequency sound that actually uses a seismic property material and travels through, right?
Mm-hmm.
Okay, in GPR, or ground penetrating radar, is radar, which is an electromagnetic wave.
Okay.
Okay, so examples of electromagnetic waves are light. So that's stuff that we have sensors we can actually see. There are other frequencies like cell phone frequencies, which are, you know, the gigahertz. You know, they used to be like 450 megahertz to 900 megahertz to gigahertz to, you know, like that. There were some frequencies. Now they're up in like 2.4, 5, I think what, 5.4, 5.2, I don't know, something like that, 5 gigahertz. So that frequency range, radar actually emits a pulse and then looks at the attenuation of that signal. Basically, as the signal comes down, it kind of gets absorbed into different materials,
Mm-hmm.
and then you see that response, like kind of like a reflection of that.
Okay, so essentially, if you've got a rock that's below the surface, and it hits it, all it is showing you that there's something there, but what, you don't know.
Yeah, so in radar you can actually, whereas there you deal with another property called the dielectric.
Mm-hmm.
So that gives you an idea of, let's see, how would I explain it? Well, I don't want to go too far into that because it's completely different
Right.
from this. But It is a nice technique to use. The problem is just like, what it's well known for is like looking for aircraft, right? Aircrafts are made of aluminum. They're conductive metals, right? And so when an electromagnetic wave at a certain frequency hits something metal like that, it bounces back and gives you a reflection, right? So that's how you look for aircraft. But the problem's different there because when it's traveling through air, the air is mostly homogeneous, meaning that it doesn't reflect things back at you unless there's like moisture in it. But so you have a very strong reflection. It's very easy to see. But when you point that thing down into the ground, you're going through a layer of like soil, and then maybe clay, then limestone, and sandstone. Hey, Daniel, this is Jason.
Nice to meet you,
Hey,
Jason.
nice to meet you.
Thank you.
And then,
Thank you.
if you want, everything's on there.
Okay, cool.
All the case histories and.
Yeah. He's recording a little bit.
I've got
Very nice.
3 other partners on the ground that, in case I don't
Yeah.
register something,
Sure, sure.
they'll be able to look at it.
Yeah, so let's
Okay.
look at the very easiest
Thank you.
problem.
Yeah.
Thank you, Jason. Okay, so we now talked about a homogeneous ground. That just means that it has the same electrical resistivity property, whatever material, doesn't matter. Okay, in this case we just look at like limestone, because limestone has an ability to create caves, and it gives us a very easy to understand situation. So we just call them voids. Let's say there's a cave here, whatever it looks like, it doesn't matter. But if it's this cave, if it's above the water table, like let's say if the water table has some depth up below it, then this is filled with air, right? And of course, air is something that we all know that at low voltages, the electricity does not want to flow through it.
Right.
For example, I mean, at 110 volts, you know it doesn't flow through there.
Mm-hmm.
Because you can, unless you touch the terminals, you're not going to get shocked, right? Even at 220 volts, right?
Mm-hmm.
Okay, well, the dielectric of air breaks down at very high voltages because you see that in lightning, right?
Okay.
Very high voltages will create a plasma path and electricity will flow through that conductive path. Okay, all these things are well known inside physics. But for the layman, it's very easy to understand that air is not conductive, right? So what happens with this electric field that was uniform? Well, instead of, let's say the electricity is coming this way, instead of going through it, it has to kind of divert around it, right?
Mm.
So now it causes this kind of ripple in the electric field, right? And from here it wants to go around it like this, right? So now you remember that those lines that we said had to be perpendicular?
Mm-hmm.
So now instead of being perpendicular, they have to kind of go like this, right? Because to be perpendicular to these lines, right? Now do you see that distance right there increased? If I were to remove this would, these things would come back. So basically if I were to measure 1 volt across these ones, so it would be, a longer distance on the surface to measure 1 volt. So if I had the spacing, I would be measuring less than that, right? So that basically just means that we're measuring this potential field here with these field lines. I know it's not, it's a little bit difficult concept, but the idea is this. If it was a conductor, then the electricity, instead of trying to avoid it, let's say it's full of water or clay, then as the current field line comes here, it wants to dip into it. So basically more charges want to avoid this, creating a denser electric field here, and therefore the potential field lines start diverging at the surface.
Okay.
Okay, and then in the opposite case, let's say that this void is now, so we'll have the same void, but now it's water, right? Everybody knows not to take a bath with a toaster, right?
Right.
Because that's dangerous for you. Okay, so here, instead of this field line coming over here, now it wants to take a shorter path, right? Where at least a path that's less resistive, right? Okay, so one thing I should explain to you. Resistivity is kind of like it's not resistance. Resistance is defined over like an infinitely thin wire and of some length, and then you can measure like with a ohm meter, right? But so what we do is we separate the transmitter and receiver into 4 probes rather than 2. So resistivity is like an average of the property of the ground. So it's not, we don't get like some resistivity value right there. Because you can see that we're transmitting current and we're measuring the potential field. We calculate that later through finite element analysis, and that's what we call inversion software. So anyway, on a crude drawing here, you'll see that these lines will start to dip into it, and then of course they distort this electric field. Well, these all have to come back there. They can't end in midair. And of course here, like this, and of course here it wants to dip back in. So we can actually put electrodes, in boreholes also, and measure potential field on here, which brings you close. But anyway.
Why would you want to put it into a borehole versus just?
Well, because we want to get closer. We want to define the electric field as close to our targets as possible. So if this void is really far down, you can see that the effect will be less and less at the surface, right? And the other thing you can say is that if it's very small, the affected electric field will only be seen when you're close to it. Remember you asked me about a couple inches of amber, like can we detect that? Well, the practical answer is no, but the realistic answer is that it depends on the scale of the measurement. If it was very close to the array and this array is on the order of centimeters, yes, you could detect it, but that wouldn't work for your application. So in any case, so now if you look at this, the field lines, do you see that the perpendicularness of it kind of goes like this now? So now instead of diverging, it actually, now you're measuring a higher voltage on the surface, right? For I get the same distance. So we do this thousands and thousands of times. That's what the machine does. It automates this, creating an electric field and measuring the potential field. And we try to, cover the entire spread of electrodes across some area. And we can do this in 3 dimensions too. It's very analogous to what you see in MRI. But in MRI, it's magnetic resonance imaging, so they're dealing with resonating magnetic fields. Okay, the mathematics is very similar because they're solving the same type of solutions. But the difference is that the doctor, we have a lot of experience with people's bodies, and so we know where the human body, where all the features are. So we have a really good starting model. If we know the nose is in the center, we know the eyes are here, the ears are here, we can start a model, give the computer a starting model that's very similar to your body type, and then it just has to perturb very small differences. So the calculations are fast enough so you can get a good 3D image. For us, we have no idea. We have no information on what the ground is like because it's different, it's unique in every location. Because it was, the way that the geology appears is because of the history of how all those sediments were deposited and how those rocks were formed, and it's completely different in every location on Earth. So, okay, so now when you have this idea in mind, so the things that we care about here are very few things. To be able to calculate this, and we'll create, the computer software creates this mesh, and actually the mesh is, you can imagine it goes divided, it's basically half. Anyway, it goes like this and like this, and then mathematically to infinity this direction, and mathematically to infinity that direction, that direction. And then we compute this using partial differential equations. We compute the resistivity of each one of these blocks, right? Then we end up with a resistivity. All right. So to do that calculations, we need to know the current of the transmitter. We need to know the voltage of the receiver, and the voltage of the receiver, is any location you're measuring the voltage, right? And then we also need to know, we have 4 electrodes in every measurement, right? 2 to transmit and 2 to measure. So we need to know the locations of those. So we need to know the coordinates of A, B, M, N. That's all we need. And then we calculate a resistivity distribution that will fit the data that we have. And I'll show you that in our software. It will become more apparent then.
Okay. Quick question.
Yeah.
So, A and B is sending the signal, and M&M is receiving it.
Yes.
These are what do you call these?
Electrodes.
Electrodes. If you're putting
Yeah, they're like
on the-
stainless steel stakes.
Right. So you're putting them in the ground.
You hammer them in,
Okay.
or if it's soft, you can just push them in.
Right.
Yeah.
So, in order for this to work, or the way I'm seeing it at least. So once you take one measurement here, you would move this whole setup here, one over until you measure the area. Is that how this?
So that's how we used to do it. Geophysicists used to do this by hand. And I can tell you because I've done these surveys myself by hand, they take a long time to move 4 stakes. If you think of the survey area, in your case you're thinking like 150, 200 meters, but in many cases my clients do things like on the order of kilometers, like several kilometers because they're looking for huge mineral deposits, several hundred meters down. And what they do, if you were to do that manually, can you imagine just walking a kilometer there? That takes time, right?
Right.
I mean, to run a mile, you know, when I was young, it was like 6-minute miles, right? Now, 10 minutes, right? To run a mile, that's 1,600 meters. But to walk one through rough terrain, and you have to go back and forth, measuring on these things, and you have to coordinate 4 guys, one at each location, make sure he actually moved to where he was supposed to be. Because if he didn't get the signal on the walkie-talkie to move to the next location, then the calculations will all be wrong, right? So what we saw was an opportunity there to automate this. So we lay out a cable that connects up to every one of these stakes.
How many can you run on one cable?
Well, you could run thousands if you want, but practically our systems are in the order of 28, 56, 84, and 112.
And then the distance between each stake is depending on what you want.
It depends on your
resolution?
application. So you were thinking about the parameters that you're thinking. This is what I ask the client, what are you looking for? How deep? And what's the resolution that you need to see? So when you tell me the resolution is, 5 centimeters, I'm going to say that's not going to work. You're not going to directly detect that.
Well,
Let's say you want 30 meters, right? So let's work that out, exactly how I approach this.
So the maximum is a 30, but what we've been finding in the last couple of weeks is 15 to 20 is where a lot of it is intense.
So I would, so the approach would be that I would get a cable that could make 30 meters, but then use close to spacing up.
Okay.
Yeah, that's the way to do it. So there's a give and take on the number of electrodes because you're paying basically for number of electrodes because it adds more cable, it adds more electronics for each takeout, right? And you're going to want to balance that cost with actually what you can achieve with it.
Okay.
An unlimited number of electrodes at the surface is not going to increase your resolution at depth. It will somewhat, but the thing is that the depth is associated with the spacing between your transmitter and receiver. If that receiver moves out here, it becomes very resolvent actually. So, that separation distance, or the separation between here and here, from the end to B, that's what gives us the depth of penetration. So if we increase this electric field we're still sending out the same amount of current, but we're just moving the location out further, then the voltage here will start getting smaller and smaller and smaller. At some point, you reach a signal to noise level where the signal can't be distinguished from the noise. Okay? And in automation, we try to do that. We try to define that point beforehand, because we know that once you get to a certain ratio, you're most likely not going to collect very good data anymore because it becomes more susceptible to noise. And so instead of wasting time trying to collect, these unreadable measurements, we reduce that to something you can do in several hours or days work.
So the distance in between your, what did you call this? The one that sends the signal?
The transmitter?
The transmitter.
Yep.
And between the receiver is what gives you the depth.
Yes, it's a relationship in depth there.
Okay. And then the distance between the stakes gives you the resolution.
Yes. Okay. So the distance between stakes, this is what's called sampling theory, and it's not unique to us. It's anytime you want to sample anything. For example, if you're measuring a waveform or you're measuring distance or things like that, it all falls under a thing called the Nyquist frequency. The sampling theory was defined by the scientist. And so what he said basically was that if you were to measure here, you would not be able to define anything smaller than half of that spacing. for example, if you're measuring a sinusoidal wave like this, if you measured it right here, you wouldn't be able to define any frequency smaller, you know, than one wavelength. And so that gives you half of that spacing right there. So if that's 1 meter, then your resolution is half meter. As a matter of fact, you remember I was drawing this grid here? I was drawing in between, on, in between, on. So we don't even try to calculate a smaller resolution because we know there's a limitation inherently in this. You can't get past that. It's a limitation of our technique.
So it was the distance between the stakes, the resolution is gonna be half of whatever that distance.
No better than half.
No better than that.
Right. So another way to say that is the resolution is half the electrode distance. Basically, that if you were to see, if the computation came up with some feature that's smaller than that, it's not real. Because we can't define anything
Okay.
below that. You know, basically what it means like this. Okay, if you have this point and this point, right? And between this point, right, you could define that wavelength, right? Or you can define a wavelength that would be twice that. That would be like that. Or I'm sorry, frequency, because this is like one cycle. Or let's say if we did, you know, we don't know what that measurement is. I mean, we could draw an infinite amount of frequencies here, and we can't define those. So what we can do is just the largest one that will fit within there. So here, I'll write this for you guys so you can see this. You can read up on this. Oh, I can tell you a good analogy where you've seen this happen, right? Okay, everybody's seen a wheel, right? Spinning wheel. Right? You're driving down the road, right? You notice the rotation looks like it's going backwards?
Right.
Yeah, so that's like your sampling of that wheel. Your brain's working to see the rotation, and it actually samples it where you get a thing called aliasing. And that basically makes, you know, it gives you these kind of false images of rotation of that wheel. It looks like it's going backwards rather than forwards. It's the same thing you get when you're timing your car and you have a strobe light, right?
Mm-hmm.
And so the strobe light is set up to, every time the ignition goes off, it pulses, right? So then your timing mark is right here, right? And then you start seeing the timing mark starts moving this way and this way. So they're using aliasing in order to time the car correctly with the pulses. So, I don't know if that makes sense.
Kind of.
Okay, okay. But let's break it down.
Excuse me, I think that's me going off.
You know, these are all things that
Mm-hmm.